With an ultra-short, highly intense X-ray pulse from a free electron laser, a nanoparticle can be imaged by recording the elastically scattered photons in the far field. The resulting diffraction pattern encodes the geometrical information about this particle. However, while irradiating the particle, a nanoplasma is formed and our sample is destroyed, driven apart by Coulombic forces. We were interested in how radiation damage occurs and on what timescale. With an infrared laser pulse, we initiated radiation damage in individual xenon clusters and imaged the particle expansion with an X-ray pulse at varying time delays from pico to nanoseconds. For each different time delay, over 1,000 images were recorded. As we increased the delay time, the diffraction patterns became blurrier, and we recorded less elastically scattered photons at high scattering angles. Less high-angle scatter is correlated to a softening of the surface when the particle becomes ionized and outer layers explode. This occurs at the picosecond timescale. On the nanosecond timescale, when our ionized particle has recombined to neutrality, speckles appear in the diffraction pattern. This had not been seen before from xenon clusters, so we asked ourselves, how can we extract the particle information from these speckle patterns? When the density in the particle drops below a certain threshold, the concentric rings of the diffraction pattern morph into a speckle pattern. The average speckle size seen in the diffraction pattern decreases with increasing particle size. So when a cluster expands homogeneously, the pattern transitions from rings to speckles and the speckle size decreases. In our experiments, the measured speckle patterns exhibit an overmodulation in the scattering intensity envelope, indicating that the cluster did not, in fact, disintegrate homogeneously. Instead, our cluster fragmented with density fluctuations. And by increasing the density range, the intensity minimum shifts towards smaller angles. By analyzing the average speckle size and the angle of the overmodulation minimum from the diffraction pattern, we were able to model how the clusters disintegrate. In our experiment, we were able to measure that on a picosecond timescale, the outer surface of the nanoparticle explodes off, while on the longer nanosecond timescale, after the inner part of our particle has time to recombine to neutrality, the particle disintegrates with internal density fluctuations.